Hello. Hey everyone, can you see my screen? Can you guys hear me?
Uh, we can hear you. Yeah,
Can you see the screen?
it's still showing the notability.
Okay, let's see. Now do you see the screen?
Yeah,
Okay, thank you, Kamalakanan. So last time when we left, we reached this point. Basically, we talked about pre-coding, right? And that's where we finished off in the last lecture, right? I think we're going a bit slower, right, than usual, right? I have acknowledged this once before, but let's see if we'll try to catch up speed on this end. Okay. So mm, everyone can see my screen still.
yeah.
Okay. I need to somehow enable way of, okay. All right. So let's assume this is a scenario, right? Okay. We have, let's say three nodes, Alice, Bob, and Chris, right? Okay. I'm just showing, let's say Alice is trying to transmit to its receiver, right? And Bob is trying to transmit to its receiver and Chris to its receiver, right? Imagine these could be in access points, right? Three different access points, okay? Nearby placed, okay? The problem is that when Alice transmits, the same signal also goes to Bob's receiver and Chris's receiver, okay? Right? And if Bob starts transmitting, that will also go to Chris's, or sorry, receiver, right? Okay. So the way to think about this problem is that now remember, right? Bob's receiver has two antennas, right? So it has essentially two axes of dimensions. Okay. Sorry, I'm just gonna write true. Okay. So one is antenna one here, right, on the receive side, and antenna two, right? So it can kind of separate two variables, right? And this could be like one could be Alice's interference, okay, and one could be the actual Bob signal, okay, right? Similarly, Chris, right? He can have one interference from Alice, one from Bob, right? And one stream from Chris, right? Would this system work actually? Are we missing something here? Someone? What would happen in this case if as soon as the Chris starts transmitting? Signal from Chris will also go to Bob and to Alice, okay? Neither Alice nor Bob, right? Okay, can keep up. So they will essentially lead to an interference, right? But not only that, even Bob's signal going to Alice receiver will also kill the Alice's signal. Okay. Everyone with me on this? Kamlakanan?
Yes, Professor. Yeah.
Okay. So question is, what is the best thing you can do here, right? When you have Alice, Bob, and Chris, right? What is it that we can do? Okay. So the first concept is we can do nulling. Okay. So remember, right? Bob is only using one antenna to transmit data, right? It can use the other antenna to somehow construct a null, right? At Alice's receiver. Okay. So to understand this setting, right, signals cancel each other at the way you pre-code here, right, such that you essentially end up canceling the signal at Alice's receiver, right? So let me write down a little bit of the mathematical equation here. Let's say alpha x and beta x are the transmitted signal, and let's say h1 and h2 are the channel gains, right? So our condition is that we need to impose this, right? What we are saying is that alpha and beta should follow this proportionality, okay, right? So as long as alpha and beta have this proportionality, that's all good, right? Okay. What is the other condition for this to work?
When alpha is H2 and beta is H1. Uh,
No, I think that
there
I
is
think you can solve for. I don't think I trust you have the capability and skills that alpha over beta should be this, right? Okay. But here's a problem, right? What if, let's say this is your H3 and this is your H4, okay, right? Okay. See, the point I'm trying to make is that basically your this alpha beta ratio should not create nulling to this Bob's receiver as well. Okay. So this alpha beta choice, right, should not create a null here as well. Okay. Does that make sense to everyone?
yeah.
So more specifically, right, what we are saying is that when you choose alpha and beta, this should be non-zero. That's also another condition here. So when will this happen?
When the channel between Bob and Alice and Bob's receiver is like linearly
So this
independent.
is Alice's receiver, right? Okay. This is Bob's receiver one. It's Bob's receiver two, right? Okay. So Alice's receiver has channel H1 and H2 from first and second transmitter, right? Okay. This is your transmitter one and this is your transmitter two. Okay. You can have H3, H4, H5, H6. Okay. So now, can someone tell me what the condition is? Condition is that when you multiply alpha comma beta with this, right, only the first entry should go zero and other should be non-zero. Okay. Everyone clear on this? Yahweh?
Yes.
Wow, good. You unmuted. You had a question there, or you just unmuted because I asked?
No, I don't have question.
Got it. Okay. So now, if I were to do nulling, right, what can I do in this case, right? So let's take this example again. Alice is sending its signal, right? Bob is sending his signal, but he's also trying to null here. Okay. So this is now another new concept. Okay. See, last time when we studied the degree of freedom from receiver's point of view. Okay. Now, what we are going to study is that alpha and beta's ratio now is very much fixed because you want a null here, correct? Okay, let me just show you an example. So let me here, right? Okay. So let's see. Bob can null at this Alice. Okay. By using 1 degree of freedom, right, and sacrificing 1 degree of freedom, it can null here. Okay. Now the other degree of freedom, it can just essentially send its signal to this particular receiver. Okay. Right. Now let's take an example of Chris. Right. Chris has 3 antennas. Okay. It has to null at Alice, right? And it has to also null at Bob, correct? Right? More specifically, right? Okay. It has to null at Bob on 2 antennas. Okay. Not just on 1 antenna. Okay. So in order to null this, right, Chris would need how many? 3 degree of freedom, right? All of these 3 degrees of freedom will be used to null. Okay, so let me write it down as an equation. Okay, so in this case, for example, right, see, my thought process is I wrote down these channels, right? Okay, these channels are, this is your antenna 1, 2, and 3. Okay, and this is your receiver 1, 2, and 3. Okay, so H11 is channel between these two, right? H21 is channel between these two, and H31 is between these three. Okay, so essentially this is the first equation. What it's saying is that you essentially have alpha, beta, gamma, right? All of them are transmitting Z, and this should give you the null. Okay, same thing for this second guy, same thing for the third guy. Okay, so what does it lead to? If you have three equation and three variable, right, they will lead to this solution. Okay, most trivial solution. Okay, what does it mean, right? It means that transmit nothing really. If all of these alphas are betas and gammas are zero, right? Okay, it leads to no transmission at all. Everyone following this concepts of degree of freedom on transmit side? Kai, Andrew.
Yes.
Yeah, yes, Professor.
Okay, good. So now remember I taught you this last class, right? See, I can present on the receiver side with this representation, right? Antenna one, if I only have one antenna, right? Okay, I will get one signal in this direction, right? If I have two antennas, I will get one here and one here to represent, right? So this is my received signal, okay? And similarly, if I have three antennas, then I can represent the received signal as a three-dimensional vector, okay? So can someone tell me how does IQ fits into this, right? See, now you already have your assignments and you have been looking at I and Q sample data, right? Okay. Even with one antenna, you have I and Q, right? How does that fit into this context? Andrew?
So you'll only have the eye for one antenna.
No, but one antenna can have two I and Q, right? Each antenna is supported and connected to one I and one Q, right?
Uh, I'm not sure.
In
So
the
good, yeah.
like antenna one case, it would turn into like a plane, so you have like 2 degrees of freedom instead of just one. And like for each of these, they're like double the amount of degrees of freedoms you have.
Nope. So these are two independent things, okay? People often confuse, or you can confuse IQ with antenna space. It's two different things, okay? One is time or frequency domain, right? Okay, IQ, right? The other is really space domain, okay? It's like it's like two different spaces, okay? Right? Either you can think of it as an I and Q, or you can think of antenna space. Don't try to mix both simultaneously, okay? Or at least you can't do it with a phasor representation, okay? So hopefully that was okay, satisfying answer. But if not, I think your assignment will essentially make sure that you understand this concept, okay? So let's take a look at an example, right? So if I have a two antenna receiver, right? Okay, and let me clarify here, right? Y1 is received signal from one of the antennas, right? Okay, Y2 is another antenna, for example, okay, right? Remember, they are also orthogonal. I'm just drawing it in a different space, okay? So you could have this kind of example, right? Okay, where y1 and y2 are this, and overall vector y is represented like this, okay? Now, in order to, let's say, if I want to do, let's example this, right? Okay, let's say alpha beta is a pre-coding here. Okay, so how does alpha beta act on this? So let me show an example, right? So let's say, right, see, we know y1 comma y2 is equal to h comma x. Okay, right? And in this case, right, x is actually not, rather x1 and x2 here. Let me write it this way. So here that's actually this. Okay, right? See, what is that saying? This is saying that you can rotate the transmit symbol. Okay, everyone with me on this? Anyone following me or no?
Yeah, I have a quick question.
Go ahead.
So x is a vector or is just a number?
X is a number now.
So you're assuming like two antennas are transmitting the same thing.
Yes, as I showed here. So what happens if I choose alpha beta to some different value? Okay, I can rotate this transmission. Correct? Everyone follows this concept? Pre-coding is that I can rotate in my received symbol. Okay. Everyone following this?
I have a question. So how do we understand the rotate meaning here? So we just times the eta and gamma here.
Sorry, can you repeat that?
So how do we understand the rotation here? So we just times the eta and the gamma here. So yeah. So how?
Yeah, I think that's a good question. See, basically what you do is really, see, by amplifying some, let's take an example. Actually, let's do following. Okay, let's say, see, this is a contribution of x. So let me call this, right? Actually, this is a better way to do it. Actually, I have a better way to do it. So let me explain, right? See, y1 is received signal 1. Okay, right? And here I'm going to call it following actually. Okay, let's see. Okay, so I can consider this antenna space as a transmit antenna space. Okay, right? So for example, this is your x1 and this is your x2. Okay, so y1 is really some negative component of x1 and some positive component of x2 combined together gives you y1. Okay, right? So this is in the transmit antenna space, right? Okay, I am showing y1. Okay, similarly, I am showing y2, which is just a single value, right, as a composition of x1 and x2. Okay, right, and that's here. Okay, everyone clear on this? Now, if this x1 and x2 are like alpha comma beta, okay, what it says is that you are scaling this axis by alpha and this by beta. Okay, so essentially you're rotating or you're stretching, like one you're squeezing in and one you're squeezing out, right? You can do that, right? Does that give you a better intuition, Kai?
Yeah, yeah.
So here, right, by choosing different gamma and eta, right, okay, I can stretch this axis and squeeze this axis, and that way I can rotate things. Okay, so to sum it up, okay, antenna space is one not limited to receiver only. You can write transmitter or receiver, right, and you can rotate things, okay, by rotating in transmitter space. Okay, Now, let's take an example, right? Now I'm going to go back to receiver space. Okay, it's no more a transmitter space. Okay, or actually we can work it anyways. Okay, we'll just consistently continue with this space actually for now. Okay, so in this example, right? Okay, I1. So let me explain one concept of alignment. Okay, let's say there are two transmissions. Okay, one is I1 and one is I2. Okay, right? And there is a wanted signal. Okay, right? Now somebody want to tell me what this is actually? So this is your receiver antenna space. Okay, this is your Y1, this is your Y2, for example. Okay, now your goal is you want to rotate I2. Okay, so let me explain if you rotate I2, right? So if you align I1 and I2 in the same direction here, okay, right, then they will act as a single interferer, right? Everyone following this concept of interference alignment? So one intuitive way to think about this is following. Okay, see, you can have your transmitter which was here, right? Okay, you can rotate the transmission signal to here. Okay, how do you rotate? You take some power alpha beta, shift them. Okay, so that it essentially stretches one of them and expands y1. So in this particular case, right? Okay, you can potentially have this rotation be done with stretching y1 and like squeezing y2. Everyone following? Actually, I have a better representation for this actually. Okay, uh, let me do one other thing actually. I think this probably will help. Okay, so first, do you at least get the intuition of what alignment means, right? And why is this impactful here before I move on to a geometric concept here? Sanjeev?
Yes. Here, the channel matrix would also give some rotation to each signal, right?
Yes. And on top of that, you can apply additional rotation is what I'm explaining, right? And
Right.
that can allow you to move signals, right?
Okay, got it.
Kai, does
So,
that make sense? Sorry.
so I1
Good.
and I2 are unwanted signals, right?
Sorry, I1 and I2 are?
Unwanted signal.
Yes, unwanted signal.
So they're sent from a third or like another transmitter you don't want. Yeah.
Yes,
Okay.
yes, yes. So let's take an example, right? In this example, right? See, the problem was in the previous case, right? What happened was that these three receivers, when you tried to null, right? All the degrees of freedom of Chris were destroyed. Okay. It essentially led to alpha, beta, gamma to be zero. Correct? Now, in this case, okay, what can we do? What we can do really is that following. See, at Bob's level, right? Okay. What we can do is we can align Alice and Chris's signal. Okay. See, note, Alice signal can come anywhere, right? Okay. And what you do is that you ask Chris to rotate his signal so that he can align with the Alice's signal. Okay. Right. And I will go over the math of it. Okay. But intuitively, this, right, breaks down the alpha beta zero. It no more needs that alpha beta to be zero. Let me explain and show you this with an example. Okay. So now if you could achieve this, right, then you have two equation, two variable, and you can suppress this interference and you can decode Bob. Everyone following? Kai?
Not completely.
So let's take an example. Okay. Actually, let me write down some equation. Maybe that will help you. Okay. So idea intuitively is very simple. Okay. See, the problem is there were three: Alice, Bob, and Chris, right? At Bob, right? If Alice and Chris don't align, okay, then Bob cannot decode his data. Okay. Because it's essentially either you null or you can align, right? Okay. Now, what Chris does is that instead of trying to null his signal to Bob, he thinks of aligning signal with Chris, right? Now, what does it mean, right? What it means is that following the contribution to Y1 and Y2, those are the Y1, those are receiver 1 and those are receiver 2. Okay. From let's call it Alice signal as A, right? And Chris's signal as C. Okay. Right. The final coefficients, right? Alpha and beta are same. Okay. For both Alice and Bob. Okay. So this ratio is same, right? Meaning they have alpha contribution here and beta contribution here. Okay. And they can be scaled up versions of each other, right? So they can have some additional gain, like some, this can be 10 times alpha, this can be 10 times beta for some reason. Okay. Right. So if you have this, right? Okay. Let me just make sorry, I think let me just erase few things. Okay. Right. Okay. So if I have this identity, right, plus I have some like Bob, right, which is like some zeta and neta Bob signal B. Okay. Right. Okay, Kai. So for all practical purposes, right, I can write this as Y1 is equal to A plus C times some 11 times alpha. Okay. Right. And I can write Y2 as 11 times beta of A plus C. Okay. Plus gamma B and gamma neta. Correct? Kai, following this?
Where does the 11 come from?
I just said it's 10 times beta, right? Okay. 10 times beta. Oh, sorry. My bad. My bad. My bad. My sincerest apologies. Okay. So it's actually this way. Sorry. My bad. Thank you. It's alpha 10, 10A and beta. Come on, guys. You guys also need to keep up. So, or don't sleep, guys. Okay. So now this is correct. Thank you, Kai. Okay. Makes sense? So this is all unwanted signal. Okay. I don't care if I decode this or not. Okay. I just want to cancel this out, right? So what I can do is I can do beta times y1 minus alpha times y2. Okay. If you multiply this with beta and this with alpha and subtract them, right? This will get cancelled. Okay. And you will be only left with, sorry, my bad again. I wrote it bad correctly, incorrectly. Sorry, my bad. This is neta times b, right? Okay. So I can multiply beta and alpha to this and subtract, right? And this will be left with only b. Kai, following this? Andrew? Sorry, go ahead, yeah, Kai.
So I don't understand where the 10 come from. So alpha is from the transmitter or the receiver, right? So in the transmitter, you're sending alpha and beta A, right?
So
And
think of this is your channel, okay? This is your channel, okay? Channel from Alice has 10 alpha on receiver 1 antenna, okay, Y1. Channel from Alice has 10 beta to this second antenna, okay, right?
yeah,
Does that
yeah.
make sense, Kai?
So you're analyzing Bob and A and C. C is the signal from Chris and A is signal from Alice. And Alice has two channels to Bob, right? So one is 10 alpha, the other is 10 beta.
Right.
Okay.
So what I made an assumption is that the channel between Alice and Chris are aligned. Okay, right? The question is, how do you achieve this alignment for Chris? Because Alice has no more antennas, it has only one antenna, it cannot rotate anything. But Chris can rotate its signal. Xiaowei, following this?
Yes. So the main idea here is we instead of nullifying three people, we just do the alignment here, right?
Yes. We null to Alice from Chris, right? And we do aligning to the Bob. Okay. So let me write down some equations for the nulling and the alignment. Okay. See, nulling gives you this equation. Okay. Now again, this is 1, 2, 3. This is 1, 2, 3. Okay. Right. Again, you're transmitting alpha times Z, beta times Z, and gamma times Z. Okay. Right. And let me write down this as 1, 2, 3. Again, 1, 2, 3. Okay. Now the next equation is for aligning, right? What am I saying? I am saying H1 L2, right? This is your signal from Chris. This is a signal from Chris as well. Okay. And what I'm saying is that it has to have proportionality of gain from signal to Alice. Everyone follow this condition for aligning? What does aligning mean? Aligning means that if this is your receiver 1, right, Bob's, okay, and this is your receiver 2 for Bob, right, the coefficient Alice creates, right, HA1 and HA2, right, this is your HA1 and this is your HA2, okay, right, should be same or in same proportionality, right? It can be same scaling factor, okay, but Chris's signal should be also in the same axis, okay, and this is Chris's signal on the left side. Warren, does that make sense?
Um, the oh yeah, I get it. So it's like as long as it's aligned, then it means that we can treat it as like one signal. And
Yeah,
the
aligning something in space or vector space, right, is means that one is a scaled version of the other. Okay. Kai, does that make sense to you?
Yeah, I understand the basic idea. But some details we cannot. I don't get it. So what is HA1 and HA2?
A1 is this. This is your A, transmitter A. It's channel between Alice to antenna 2 and Alice to antenna 3.
Oh, okay.
Actually, it should be A2 and A3 for that practical purposes. Okay. So that it's clear that way. Sanjeev, is this clear to you? Kamla Kanan?
Yeah, so we are having two receivers, but three unknown equations. So somehow we are trying to make two sets of equation. Is that correct?
No, first, this is an interference alignment equation. There
Yeah.
are two equations. This is an equation of nulling. Hopefully, this is clear enough to everyone. Okay,
Yeah.
right? What is interference alignment? Interference alignment is that when you have signals in spaces, right? Like a signal on two antennas, right? Okay, this can be written as this as a direction of, when I write antenna space, right? What it really means is that it's telling me how much gain it has on antenna 1 and how much gain it has on antenna 2 intuitively in a scaling manner. Okay. So if I send one unit signal, it will be received by this much power at this antenna and this much power on this other antenna. Okay. Now, when I say interference alignment is that you align the amount of power received on antenna 1 and antenna 2, right? Have a proportionality with each other. Okay. So does everyone follow what alignment means? Alignment means that a second vector V2, right, is essentially alpha times V1, or they are proportional to each other. Okay. Xiaowei, Kai.
I mean, say if Chris is receiving the signal, at that point there are 3 receive antennas. So is
No, there are
I
two
mean,
receive antennas. Forget
I mean
Chris's
for
receiver for now,
no no
okay?
oh yeah
Forget
yeah
Chris's receiver for now. Just only focus on these three things I'm talking about, right? I want you to understand the basics of nulling, which is happening on equation 1 or the antenna 1 of the Alice on receiver. I want you to understand next thing is alignment, which is happening between Alice and Chris's signal at Bob's receiver. Okay. Is that clear, Sanjeev?
yeah
Javed?
Yes.
Warren?
The left side of this interference or alignment equation is Chris.
Yes.
So like the alignment is for Bob receiver.
Alignment is happening at Bob's receiver. Signal is from Chris, and Chris is transmitting the signal from 3 antennas. Okay. This is why
Okay.
you have alpha, beta, and gamma, each from each antenna, and then their channel gains H12, H22, and H32.
Yeah,
Okay.
can you go back to the previous slide and let me see again when the alignment condition is met and how do you get to the signals? Okay, so Y1. See.
Clear?
Beta Y1 minus alpha Y2. Okay, okay.
See, I
Got
think
it.
you need to internalize and get away. Imagine that your received signal is a single scalar. Okay. It's no complex, no, don't confuse with complex numbers. Okay. Then think of antenna space as a complex representation. Okay. Or n-dimensional representation. Okay. See, if you have scalar numbers, right, and just think of them as a scalar values. Okay. This will all then become intuitive, right? What I'm saying is that what is alignment? Alignment is then the coefficients associated at y1 and at y2 follow the same ratio. So let's take an example. The signal or the channel gains associated with A and C follow same ratio. Okay, correct? If they follow same ratio, right, what happens is that when I do this subtraction, beta times y1 times beta times y1 and alpha times y2 minus alpha times y2. Okay, what it means is that I'm going to do beta sorry, alpha here. Okay, let me rewrite it. Okay, alpha here, right, and then whatever, right, alpha and beta here as well, right? See, these two will cancel out each other because once I subtract them, right, they will go away. What I will be left with is only signal from Bob B with these gains. Okay, is this clear, Kai, or who was asking the question? Sorry,
Yeah, it is clear to me now.
Warren.
Yeah.
But the condition really is proportionality. Okay, the channel needs to be proportional on receiver 1 and receiver 2. So this is really, I want to maybe clarify the notations here. I think the notations probably might be confusing as well. Okay, so let's see, first index is used for TX antenna, second index is used for RX antenna. Okay, and let me clean this notation up actually, so that way it's clearer actually. Okay, I'm gonna erase and I'm gonna write the numbering on this side differently. That's it. I think that's what you need. You don't need to even consider Alice's receiver. You just need to consider Bob's receiver. That's where alignment is happening. Okay, this nulling is happening at Alice's receiver. Okay. So yeah, so let me maybe change this notation so it's clear. Okay. It's confusing. This is confusing everyone actually. Imagine this is A prime for that matter. Okay. And this is all A primes here. Okay. This condition everybody understands. Okay. This is for your this receiver. Okay. Right. Everyone clear on this?
Yeah.
Now,
Yeah.
this is your transmitter index, or sorry, and let me make sure I make sure this is correct. Okay. So this is your transmitter index, first index. The second index is receiver index. Okay. So H1, what did I do? Okay. Yeah, no, this is fine actually. This is fine. So this is receiver 2. Okay. Right. Okay. I'm looking at all the channel gains from Chris. Okay. Summed up. Yeah, I think I made a little bit of mistake on the notations on some sides. Let me fix the notation. I'll fix the notation. I'll update it. Okay. So I think the notation was correct. I think the correction was supposed to be here. Actually, that was a correct correction I did. Okay. Sorry, ignore all what I said. Okay. The notation is all perfect. Okay. The only thing mistake is the right side equation. Okay. So at receiver 2, this is the equation. Okay. These are the gain values corresponding to Chris's channel. Okay. H1, this is your TX index, and this is your RX index. Okay. Similarly, this is true for the third receiver, right? So the proportionality of the second receiver to the third receiver should be same as the channel gains from the Alice's transmitter to the second receiver and the third receiver. Okay. Is this clear? Sorry, it was a little bit messy. Kamlakanan, Kai.
Yeah.
Yeah, clear.
Okay. So if you end up in, so now this essentially allows us to do basically, so now your alpha, beta, sorry, alpha is can be lead to non-zero, beta can be non-zero, and gamma can be also non-zero in this case. See, one of them is a proportionality constraint and one of them is a equality to zero, right? Okay. So you can solve all these three and you can make sure that they will lead you to non-trivial solutions, right? Does that make sense to everyone? Kamlakanan or Jave?
That also depend on that H11 and H2, right? Like a solution for these equations. What if it fails?
No, I think it's, yeah, very likely this won't that easily fail. It's very easy to get a non-zero solution. I think the question is not that actually. Question is that after doing all of this aligning, right, will Chris's signals arrive on the Chris's receiver? Okay. So I don't think this is a hard problem. Okay. So let me give you an example where it actually can be used. Okay. So so basically the point is you can have three concurrent transmission going on, right? And some of them don't even have that many antennas, right? Like even second antenna doesn't even have that many receivers. Okay. So let's take an example in this case in a really a practical sense, right? So there is an AP1, AP2. They have Ethernet between them, okay, and they are synchronized, okay. And let's say AP1 and AP2 has two antennas, same Bob and Alice has the same antennas, okay. So here's what we do, okay. Bob sends two packets, okay, right? P1 and P2, okay, right? to his AP. Okay. Alice tries to send another packet. Okay. Can Alice send this another packet? Can somebody answer this? Or what is the, I think the answer is on the slide, but at least you guys can understand and tell me what the answer is. So what's the first thing to do? So will alignment or interference, will alignment be sufficient in this case? Let me just show it this way. See, you can take P3 and null it at AP1, right? Okay. And then just send it to AP2, okay, right? The issue is AP2 doesn't get, let's say, Alice's signal, right? But the problem is, sorry, AP1 won't get signal of Alice, right? But AP2 will get signal of Alice, but it also will get signal from Bob, P1 and P2, right? And it has nothing, it doesn't know what to do because it has two equations and three variables, okay? So that doesn't work, right? The other strategy is that P3, right? Okay, you can rotate and what can you do? So let's take an example here, right? Okay, P1 is here, P3 is here, right? And P2 is here, okay? Now, decode P1, right? What you do first is that you pick a signal which is strongest, P1 or P2, okay? And project them in the plane orthogonal to P3 and P2, okay? Right? In this case, there is also some contribution from P3, okay? So you need to really rotate P3 to P2 directions, P2's direction, okay? Once you rotate P3 to P2's direction, right, then you can decode P1 first. So you first decode P1. Then you send this P1 through this network to this receiver, okay? Right? It cancels P1 as well, right? Okay. Everyone following this? Is it clear to everyone what's going on?
I didn't get that. Sorry.
Okay, good. Thank you for telling me that. Okay. So let's go over the process again and I'm gonna erase everything. Okay. See, there is a third principle we need to use as well now. Okay. Which is interference, alignment, and cancellation. Okay. Very important is cancellation. Okay. So this is a master stroke if you think about it. Okay. And here's what how you do it. Okay. So first you rotate P3 to P2. Okay. You choose alpha beta so that whatever gain P2 has going to these two antennas, right? You use alpha beta to match the same gain values, proportional gain values. Okay. Right. So P3 then is aligned with here. Okay. Right. Imagine this does not exist now. P3 is rotated to P2. Okay. Right. Now you decode P1 first. Okay. Everyone clear on how to decode P1? It's two bases, two equations, two variables. And if P3 and P2 are aligned, you can just decode P1. Is this clear until this point? Yahweh?
Yes.
Andrew?
No.
Okay, what's not clear? Andrew, can you speak up?
Um, I'm not really sure.
I have a question. So you are looking at the signals on one antenna from AP1, right?
No, guys, I think what does this when I show this space, right? Andrew, what does this means when I show this space on the receiver side? This means receiver one's signal. This means receiver two signal, correct?
Yes.
Did you attend last class or you were not here last class?
I was here last class.
Okay, but you now know this representation of space. Antenna 1 receive, antenna 2 receive is denoted in this way, right? So Andrew, are you following interference alignment concept or you haven't been able to follow the interference alignment concept?
I mean, I see what's going on. I don't really understand the fundamentals, like why we're doing alignment.
So the reason why we are doing alignment is there is no way in this system you can send 3 packets through, okay? Whatever you do, right? So in this example, right, the best case is that Alice does nulling to AP1, right? Nulls his signal, right? And it can send 1 packet to AP2, okay? Bob can also do the nulling to AP2, okay? And send 1 packet to AP1, right? So really you got 2 packet across the network, correct? In one time slot and frequency slot, right? But with interference alignment, you can essentially pass through 3 packets, okay? Now, do you see the powerful feature of this, Andrew?
Not quite.
So do you at least understand that you can only send 2 packets with interference nulling?
Yes.
Okay. Now your question is how alignment allows us to send 3 packets?
Yes.
So the simplest way to think about is that first you guys understand that this is a space dimension, right? Okay. So I'm drawing here, this is your received antenna 1, right? And this is your received antenna 2. Okay. Now, whenever you send any packet, they have certain contribution on each of these receiving antennas. Okay. So in this case, P1 has this contribution, this much on antenna 1 and this much on antenna 2. Okay. Is that clear, Andrew?
Yes.
Now, let's say P1 is this, right? Those are his contributions, right? Similarly, P2 has its own contributions, right? Which I will use a different color, hopefully. So these are P2's contributions, okay? Right? And this is where P2 lands up finally, let's say, okay? Right? And P1 is already here, right? I have shown, right? Okay. And let me draw it again. Let's say this is your P1, right? And this is your P2. Now, P3, right? Okay, has these channel coefficient gains, okay, right? And what you do is you choose alpha and beta so that they match up with P2's contribution, like they match up to the gain values of orange one. So let's say this is your H1 and H2. So you choose H1 by H2 equals to, you choose alpha and beta so that alpha and beta kind of multiplied by, let's say, in this case, I'm going to write H3 and H4, okay, right? Okay, so really what you did is that you made contributions of P3 and contributions of P2 align on this axis, okay? So this is your P3, right? And orange is P2. Is this clear, Andrew?
Yes.
Now, once you align them, right? Okay. Let me make and look, so P3 and P2 are aligned. This does not exist. Okay. Or let me erase it for now. This does not exist because this was earlier that way. And then I adjusted alpha beta so that P3 and P2 aligns. Now I have P1, P2 and P3 are aligned, right? This is unwanted signal, right? P2 and P3. P1 is a wanted signal and I can decode P1 first. Okay. All right. Is that clear?
Yes.
Okay. So now once I decode P1, right, I send it over Ethernet, okay, to AP2. And it does is that it subtracts P1. It cancels P1. Okay. Right. Now AP2 has two antennas, right? And it has two variables, P2 and P3. Okay. Now it can decode both P2 and P3 because two antenna, two equations, right? Does that make sense, Andrew?
Yes.
Does it make sense to everyone now how we got all of these P2 and P3 decoded, right? How did we get 3 packet across? Kamla Kanan? Warren?
Yeah.
Yeah.
Jave?
Yes.
Anyone who doesn't see it clearly? Sanjeev?
Yeah, I get it.
So it's an important and very powerful concept, right? So why don't someone tell me, why can't I use AP1 to decode P2 and P3?
Because they are aligned actually after.
Yes. Andrew, does that make sense to you now?
Yes.
See, they are on the same axis, right? You don't know which is P2 and which is P3. Basically, P2 and P3 are degenerate. Remember this subtraction I did, right? Similar, like, where is this? Sorry. I wrote down this alpha beta example, right? Where is this? See, remember in this case, right? You can't decode with these two equations A or C, okay? Because A plus C, 10A plus C essentially looks one thing to you, okay? What you can do is you can decode 10A plus C here, okay? Does this clear to you, Andrew or Warren, everyone?
Yeah, that
Yes.
makes sense.
Okay. Sorry. So just wanted to, I think, let me explain one other concept, I think, which I think is extremely important, right? For us to all understand and learn, right? See, MIMO channels, right? Okay. Let's say an signal goes out in a direction theta, okay, right? So, and let's say the signal is received at, let's say, angle and some angle alpha, okay, right? Okay. This is your receiver, let's say, okay, and it has two antennas, okay, right? This is the perpendicular from the receiver's direction, okay? This is perpendicular from transmitter's direction, okay? So first, right, this ray, how much additional distance will it travel? Or let's call this as D1, let's call this as D2, okay? Or let me write it D1, D1, 2, okay? So D11 and D21, okay? So this is your D21 and this is D11, okay? So D21 is D11 plus, what is the additional distance? Let's say this is your D.
Cosine time d times cos of that angle.
Is it cos or sine?
It's okay. Okay, it's like okay, it's
So this angle is again theta. Okay.
okay, okay.
Right. Okay. So this is D and this is theta, right? So what is this distance? This is your extra distance
Extra
traveled,
distance, yeah.
right?
Yeah.
Everyone following this? Andrew?
Yes.
So that is d sine theta. Actually, it's other way around. Minus d sine theta. Because d11 is longer, d21 is shorter. Correct? Or we can write it other way around. Actually, let's keep this as d11 and this is d11 minus d sine theta. Okay, clear? How about d12 and d22? Okay, so let's keep again d22 as d22. Okay, now what in this case happens is that what I'm asking is that let's see the same thing happen to receiver 2. Okay, right? So in case of receiver 2, right? Again, I want to write everything in terms of d11. Okay, so let me first calculate d12, which is like transmitter 1 to receiver 2. Everyone with me so far? If it's confusing, let me know. Let me erase a few things here. Okay, okay, I'm gonna use a different color. Okay, so now let's take an example of d12. This is your d12, the one which is in the red. Okay, what is this additional distance traveled here? Now this angle is alpha. Okay, somebody want to take a guess? What is this additional distance? Let's say this is your alpha, right? This is 90 minus alpha. This is again alpha. Okay, so this is d sine alpha. Okay, so it's d11 plus d sine alpha. Correct, Andrew?
Yes.
And what is d22? D22 is nothing but d21, which is 2 to 1, right? Okay, plus d sine alpha. Okay, everyone with me on this? And d21 is nothing but d11 minus d sine theta plus d sine alpha. Okay, everyone with me so far? So let me now write channel matrix H. Okay, so this is exponent of minus j2 pi d11 over lambda. What is this? Everyone familiar with this notation? And why am I writing it this way? This is your lambda over d into exponent of j2 pi minus d over lambda. Correct? Everyone following this notation here?
Yeah.
Andrew?
Yes.
Okay, now I'm gonna substitute all these values in terms of d11. Okay, and hopefully I'll do it the right way. Okay, but just bear with me if I make mistakes and let me know if I make mistakes. I'm gonna write it small so that I can see the original thing. So what I'm gonna do is I'm gonna take first this following. See, everything is written in d11, right? So I'm gonna take d11 out as common. Okay, so I'm gonna write exponent of minus j2 pi d11 over lambda as common term. The first term becomes 1, right? Okay, now d21, right, is negative of d sine theta. Okay, and that becomes positive j2 pi d sine theta over lambda. Okay, because negative of negative is positive. Okay, now let's see d12. Okay, d12 is this, which is d sine alpha, positive, right? So which is negative now. Exponent of minus j2 pi d sine alpha. Okay, everyone with me? And this term here really is a little bit more longer, right? So I'm going to write it here. This is nothing but exponent of minus j2 pi d sine alpha plus j2 pi d sine theta, the entire thing over lambda. Okay, everyone clear on this? Clear, folks?
Yes.
So this actually can be written in this form. So a column times row. So 1 times 1 is 1, right? Okay. 1 times this is essentially this minus d sine 2 alpha over, okay. So everyone follow this. Multiplication is equal to this, an additional term of this exponent outside. Okay. Right. This exponent remains outside here. Okay. Everyone agrees this?
Yeah.
So let me now rewrite this further. Okay. I call this as a rotation matrix. Okay. So think of this as u. Actually, I think, did I make a mistake here? Sorry, I have. See, the alpha should have come on the left side, or should it? This is transmitter index, right? Okay, I think we made a mistake, but any case, okay, this is actually H star. Okay, that way it fixes my mistake. Okay, all right. Any case, it should have been, because it's an H star. Okay, so did everyone make? So typically, right, in most of my notation, right, I tend to follow d tx comma rx. Okay, right. I think today I wrote as d rx comma tx. Okay, and therefore I'm making this as a conjugate. Okay, uh, it's fine. You guys follow me. So in a manner of speaking, what I was trying to get to is following. Okay, the term which I should have gotten for h is following. Okay, 1 exponent of minus j2 pi d sine alpha over lambda. This is your received rotation v. Okay, I'm going to call it v star, and you have u, which is 1 exponent of minus j2 pi d sine theta over lambda. Okay, right. This is v into u star. This is your rotation from transmit direction, because if you think about it, right, theta is saying that how much rotation you can create from transmitter's point of view. Okay, right. And this gets multiplied by exponent of minus j2 pi d11 over lambda, right, times lambda over d11. Okay, so this is your channel gain, or one path. Similarly, you can sum over all paths. Okay, lambda over d path. Okay, and same thing, you can have u theta I and v alpha j, or we can call even I. Okay, some overall path. So each path has, this is what theta is, angle of departure. Okay, how the signal departed from the transmitter. Okay, alpha is angle of arrival. Okay, everyone following me so far? Andrew,
Yes.
Kamlakanan.
Yeah.
So what this is also telling you, right? Okay, if you only have one path, okay, the rank of the matrix will be this is your H. Okay, rank of H will be 1. Okay, that means that you can only send one stream if there is only one path. Okay, one stream. Okay, and tell you interesting thing. Okay, if you have to pre-code, right? Pre-coding is U star, which is inverse of angle of departure. Okay, right? And post coder, right? Or post decoding, right? Okay, is proportional to angle of arrival. Okay, or inverse of angle of arrival. Okay, is this clear to everyone? Warren, go ahead. Yeah.
We can write it as like a multiplication of the angle of arrival and angle of departure, but I get that part, but why does the rank of H equal 1? Wait, why is the rank of H only 1?
Where if you have one path, right? Okay, right? It's one path means that you have only one V into U, right? It means that you cannot have rank 2 because it's a 1 by 2 into 2 by 1, right? It's a linear
Okay.
algebra. Rank of individual matrices, if not, yeah. Hopefully this is clear. So
Yeah.
yeah, rank of AB is always less than equal to rank of A or rank of B. Okay, it's fine. You guys can figure that part out. Okay, Andrew, does that make sense?
Yes.
See, this is an extremely powerful notation. Okay, and somehow it's kind of skipped. It gives you intuition on pre-coding and post-coding if there is only one path, right? And more importantly, it helps you write in a generalized form channel matrix in this form variation, right? And you can learn and get more intuition and insights. Okay, so I was hoping to get to the next lecture and cover like capture some effect here, um, but it's fine. I guess it's what we are, right? Where we are. Any questions for today's class? I think why don't we take next 2-3 minutes to take more questions instead of going further any further.
So it's like splitting a channel matrix. I mean, like factorizing it like SVD kind of thing.
Yes, it's a kind of SVD, right? It's not exactly an SVD because remember, right? U theta i's are not perpendicular to each other. Okay, they can
Yeah.
be only perpendicular when theta i's have a 90-degree rotation between them. Does that make sense?
Yeah. Yeah.
Nice. That's a good question. Thank you. Anything else?
Yeah, about the alignment and cancellation. We talked
Kai,
about
your
using
audio
like,
still is going haywire, right? Let me turn off my video. Maybe that will help your audio.
what about now? Is it
Yeah,
better?
it's better. Yeah, go ahead now.
So about the about the alignment and the cancellation, you mentioned using the Ethernet cable to transmit a signal to the other device, right?
Right.
Why can we do that? I mean, if they have Ethernet cable, they are no longer two devices. Yeah, only one device.
So not exactly. Ethernet is actually a pervasive infrastructure, right? So I don't know if you notice, right? All of our access points are actually connected by Ethernet, right? So technically, that way you can say the entire Wi-Fi network is one device, right? If you have to argue that way. But these are distributed infrastructure, right? All of them are connected via Ethernet to the core network, right? So they have to be connected by Ethernet, right? There is no choice there. Does that help answer the question?
So can you give an example in real life that use this alignment cancellation method?
So I don't think they use it, but they can use it, right? There are some other problems with this, okay? So in real life, right, you can take, for example, like when you go to UCSD, right? If there are 5 access points on a floor, right? All of those 5 access points are connected by Ethernet to a central core controller, right? So they may not be connected to each other by Ethernet. They can be connected to one switch, okay? This is your switch, okay? I'm drawing it as a switch, right? This switch connects to all APs, okay? And this switch is one which connects to the internet finally, okay, right? So internet comes to the switch and then switch distributes it to the Wi-Fi APs, right? So technically all of the Wi-Fi APs are connected to each other and they can use the switch to send the packets to each other, right? Or the IQ samples rather to cancel each, right? So I'm gonna post the paper on this actually, Andrew. Sorry, not Andrew, Kai. You can take a look at that paper. I think that would be very, very informative and you can learn a few things from that.
Okay, I see.
Yeah, and but you can also come back and tell me what's wrong with that paper. Okay, why doesn't it work really well, right? Okay.
Okay.
Yeah.
And in the same picture, like you can, I mean, like in uplink direction, like when Bob and Alice are sending to APs, you can decode 3 packets. But can we do the same thing on the other way? Like in the AP example, Ethernet example, like we decode the P1 and then cancel it, right? Like
So
we can't do it in the other way, right? Because Bob and
yes, very
Alice.
much. This is a very good point actually. Thank you for raising it. Okay. See, if AP1 and AP2 wanted to send 3 packets downwards, right? Can we do it, Kai?
What's the question? I think.
So right now I'm considering uplink case, right? When Alice and Bob are sending the packets to APs. Okay. Imagine the case of downlink. Can you still send 3 packets in this setting, which I'm showing on this
I
figure?
guess no, because they have.
Yes, you cannot. Okay. And the reason why you cannot is because there is no Ethernet which can connect Alice to Bob. And they cannot send this P3 back on the Ethernet to Bob and Bob can then cancel. Does it make sense to everyone? It's a great point. Thank you for raising that, Sanjeev. Sanjeev, Kamlakanan, does that
That's
make sense?
Kamalakanan. Yeah.
Sorry. Oh, that was Kamlakanan? I
Yeah.
see. Sorry, no worries. My bad. It's a
And
little
one more thing
similar.
is like, how is it different from SIC, successive interference cancellation?
So SIC can further improve this. Okay. So let me make one more simpler observation for SIC. See, SIC as a technique works in frequency or time domain. Okay. This as a technique work on a space domain. Hopefully that difference makes something sense to you. Okay. So let me explain, right? See, what do you do in SIC? You take basically 2 symbols which are superimposed on each other, right? Take the one which has a higher power, decode it first, and then subtract it and then decode the next one, right?
Yeah, yeah.
See, basically, what did you do? You took the same time sample and reused it 4 times, right? Okay.
Yeah.
There is no space dependence here, right? See,
Okay.
in a manner of thinking, you can think of IAC as SIC in space.
Okay. Okay. Got it.
It's a little bit, yeah, it like requires some thinking. Here's a question for everyone, okay? What if, since Alice and Bob are 2 different transmitters, right? They will have their own different carrier frequency offsets, right? So will this still work if each Alice and Bob have their own carrier frequency offsets? Kai, thoughts?
they are not sharing same bandwidth? I mean,
They're sharing the same frequency, same time, everything. That's why we are thinking of all these things, right? If they didn't have the same frequency and same time, why would we even bother with cancellation, right?
yeah. But what's the question? You're saying that you're not transmitting at the same carrier
No,
frequency?
I'm saying that Alice and Bob has a carrier frequency offset, right? Hopefully you know what now that is, right? With your assignments.
Oh, you
But
mean
any case,
offset. Okay,
carrier
okay.
frequency offset. Sorry, yeah.
Can we adjust that also using alpha and beta?
You tell me. I
Okay.
don't know.
Okay.
Why don't you think on this? This is a really hard and really tough question to think about, okay? See,
Okay.
this will truly, truly clear up your concepts on space and frequency and time domain, okay? What happens if you have a carrier frequency offset in this particular setting? Can you still send 3 packets? And Andrew, I'm going to ask you this question next time, okay? Do I still have Andrew here?
I mean, I was talking to you, not Andrew.
That's fine, Kai. I think I was hoping Andrew can answer because he was also confused with the interference alignment concepts. So, Andrew, are you here with us?
Oh, I'm sorry. What?
Yeah, I think you need to answer the question I just asked.
What was the question?
Yeah, I think you'll have to look through the recording and then see the question and then answer. Come back with the answer.
Oh, okay.
Yeah, I think it was still before 6:20, so it counts. Okay. Anything else? Great questions, guys. Really good questions. Appreciate it. All right. I'll see you on Thursday then. Bye, guys.